Alright, this is the Beta 1 notes, and we are talking about symmetry. First thing we have here is point symmetry. Two distinct points, P and P prime. It's important to note this little apostrophe that you see here. We would say P prime. The little apostrophe, you pronounce it prime. Just means a different version of P. Two distinct points P and P prime are symmetric with respect to a point M, if and only if M is the midpoint of segment P, P prime. Point M is symmetric with respect to itself. So it's basically saying if you have a segment in which M is the midpoint, then P and P prime are symmetric with respect to that midpoint. In other words, if you were to take P and physically flip it over M, the same distance in the same direction of this segment, it would land on P prime and vice versa. P prime, if you were to go in the same direction as M and the same distance from P prime to M, you would end up on top of P. It's identical on both sides. It's a mirror image. Example A. Find the coordinates of P prime if P and P prime are symmetric with respect to point M. I would strongly encourage you to first make a small picture of this, labeling your P, your P prime, and your M. M is the midpoint, therefore it's the same distance from P to M as it is from M to P prime. Coordinates for P are -3, -3. Coordinates for M are 1, 1. As it says over here on the right, use the midpoint formula. M is the midpoint of P and P prime, so we're going to use the midpoint formula. Midpoint formula is capital M equals the ordered pair. You have the sum of the x values divided by 2, and this comma here means and. It's two separate problems. You cannot combine these in any way. We have the sum of the y values divided by 2. So when it comes time to filling things into this midpoint formula, you got to figure out what you know and what you don't know. For example, P, we'll say, is our first ordered pair. So we'll say that P is x sub 1, y sub 1. P prime, that's our other endpoint. We'll say that's x sub 2, y sub 2. And M, that is the midpoint, so there's no variables that are needed for that. When it comes time to substitute, we're saying M, we know what the midpoint is. It's 1, 1. X sub 1, we know that's -3. X sub 2, we don't know, is what we're trying to figure out. We don't know what the x value is for P prime. Y sub 1 is -3. Y sub 2, we don't know. So we have this equation, we have two variables. We actually have two equations here. We have that 1 is equal to this fraction, and we also have that this 1 is equal to this fraction. So you set those equals to each other. In other words, this 1 represents the x value of the midpoint. This -3 plus x divided by 2 represents the x value of the midpoint. They're both representing the same thing, therefore they're equal to each other. So we have 1 equals -3 plus x sub 2 over 2. And then we also have this other equation, 1 equals -3 plus y sub 2 over 2. This particular problem, it just happens to be these x and y values are repeated. It's not always going to be that way. Solving this equation down here, If we were to get rid of this fraction, we could multiply the left and right side of the equation by 2, each term. There's 2 terms. On the left, you get 2 times 1, which is 2. On the right, the 2's cancel, so you get negative 3 plus x sub 2. If you add 3 to both sides to get x by itself, you get x sub 2 is 5. Over here, it's the same equation. You solve it the same way. If you multiply both sides by 2, you get 2 is a negative 3 plus y sub 2. Add 3 to both sides, and you get y is 5. So the coordinates for p prime are 5, 5. Now it should make sense. If you look up here, since m is the midpoint, the distance from negative 3 to 1 on a number line is 4 spaces. So if you go 4 spaces from the 1, 4 plus 1 is 5. That's what we have. Same way with the y values. Negative 3 plus 4 is 1. 1 plus 4 is 5. So the answer makes sense. You have an option right now. Your option is to pause the video, do problem number 2, and then unpause it and watch how I did the problem. Feel free to fast forward if you just want to check your work real quick. If you need extra help, then don't fast forward. Your other option is, I'm not comfortable with this yet. I want to see another example before I try one on my own. Doesn't matter to me. Do whichever one you'd rather do. Same directions. So I'm going to draw a picture. I'm going to put P on it. The letter P, pardon me. I'm not going to do anything crazy on it. I'm going to put M on it. I'm going to put P prime on it. P is negative 2, 3. M is negative 4, 5. P prime, we don't know what that is. So I'm going to say that P is x sub 1, y sub 1. And that P prime is x sub 2, y sub 2. Use the midpoint formula once again, which is m equals the average of the x values followed by the average of the y values. The midpoint is negative 4, 5. My x values are negative 2 and x sub 2. My y values are 3 and y sub 2. Now once again, this negative 4 is equal to this fraction. It's the first number and the ordered pairs are equal to each other. So we get negative 4 equals negative 2 plus x sub 2 over 2. And we also have 5 equal to 3 plus y over 2. You solve each of these. This first equation, if you multiply both sides by 2 to get rid of the dividing by 2, on the right the 2's cancel. On the left you get 2 times negative 4, which is negative 8. On the right you get negative 2 plus y sub 2. If you add 2 to both sides, you get negative 6 for your y value. On the right, if you multiply both sides by 2, 2 times 5 is 10. 2's cancel on the right side of the equation. And to get y by itself, you subtract 3, and you get your y value of 7. Pardon me, I just wrote negative 7. It's positive 7. At this point, I'm asking you politely, pause the video, do problem number 3. Whenever you finish it, then go back and either watch the video or just check the answer, compare your work real quick to see that it's the same. Alright, number 3 would do it the same way. We got P and P prime are the endpoints. We got M as the midpoint. Coordinates for P are -4, 6. Coordinates for M are 3, -1. Coordinates of P prime we don't know. Coordinates for P we know. Also variables represent those same things. I'm just going to write that down. Midpoint formula is the average of the x values followed by the average of the y values. Midpoint is 3, -1. X values here we have a -4 and x sub 2. Make sure when you substitute numbers use parentheses like this -4. Y value is 6 and y sub 2. So 3 is in the same position as this first fraction. Therefore, 3 is equal to -4 plus x sub 2 over 2. If I multiply both sides by 2, I get 6 is -4 plus x sub 2. If I add 4 to both sides, I get x sub 2 is 10. So the x value of P prime is 10. Second equation, I got -1 is equal to 6 plus y sub 2 over 2. If I multiply both sides by 2, I get -2 equals 6 plus y sub 2. Therefore, -8 is y sub 2. -2 minus 6 is -8. We continue here to the next page. So we just talked about symmetric with respect to a point, point M. This is more specific, symmetric with respect to the origin. The origin, you'll recall, is where the x and y axis intersect each other. The graph of a relation S is symmetric with respect to the origin. It's the ordered pair 0, 0. If and only if -x, -y is an element of S, whenever xy is an element of S. A function f of x has a graph that is symmetric with respect to the origin if and only if f of -x equals -f of x. It's a lot of words, it sounds confusing, but it really is not that difficult. This is a quick example. Right here we have the origin. Let's say we have an ordered pair. -2, 1. Let's call that point P. The point that is symmetric with the P with respect to the origin, notice it says here -x, -y is an element as long as xy is an element. What's happening here is the signs are being changed. So if this is -2, 1, if I just change the signs to +2, -1, +2, -1, that's where P prime is. At another point, such as, I don't know, -5, -2, and let's say that was Q. Q prime, I just change the sign, so it'd be +5, +2. I go to the right 5 and up 2. Now this is saying these aren't just points, this is an entire graph. If you can pick any point on your graph and change the signs of that point, and that point is also on your graph, that means that graph is symmetric with respect to the origin. Next we have line symmetry. Two distinct points, P and P prime, are symmetric with respect to a line L, if and only if L is the perpendicular bisector of P, P prime. A point P is symmetric to itself with respect to line L if and only if P is on L. So let's check this out. point P, here's point P prime. It says these 2 points are symmetric with line L, if and only if L is a perpendicular bisector. So let's say this is L right here. We have this segment connecting P and P prime, which may or may not be in the picture. Once again, these points are symmetric with the line L if line L is a perpendicular bisector. Perpendicular means forms a 90-degree angle. Bisector means it's the same length from P to the line as it is from P prime to the line. Once again, it's a mirror image. Things are identical on both sides of that line. Let's look at example B. I need to fix some of these a little bit because when I transferred this into the software, it didn't come out very well. The graphs below are portions of complete graphs. Sketch a complete graph for each of the following symmetries with respect to the line, the x-axis, and then the y-axis, the line y equals x, and the line y equals negative x. Let me first fix this a little bit. This is supposed to be where my y-axis is. This is supposed to be my x-axis. So here's our graph. This is our main graph that you see right here. So for part A, I want you to make a complete graph. Now a complete graph is going to include the part that you already see there. If you notice, it starts at the origin, and then if you go left 1, 2, 3, 4, 5 and up 2, there's another point. So if I go left 5 and up 2, looks like I'm about here. So this is the original part of the graph. Just repeating it. Now part A says with respect to the x-axis it's symmetric. So let me make sure that you can see my x-axis. This is the x-axis. So if you were to take this ray that you see here and reflect it over the x-axis, where would it fall? Well, it would fall right here. Now, if you get good at this, you can just look at it and know where it's going to go. If you're not good at it yet, let me try to give you some guidelines on how you can do it. According to the definition that we just read about line symmetry, 2 points are symmetric with respect to a line if that line is the perpendicular bisector of that segment. So for example, if I pick a point on this original ray, like right here, it's approximately left 5 and up 2. It's the point that's symmetric with that, with respect to the x-axis, be the same distance that that point is to the x-axis. Has to be perpendicular, 90-degree angle. That distance is 2. Because we have to go up 2 to get to this 2 here. If I repeat that down here, if I go in that same direction, perpendicular, I have to go down 2. That puts me at negative 5, negative 2. This point here at the origin is on the line of symmetry. It says a point P is symmetric to itself with respect to line L if and only if it's on L. So since this point, we'll call it P for illustrative purposes, since this point's already on that line, it is already symmetric with respect to itself. Since we know this is a ray, you connect those 2 points and that gives you this ray down here. Let me show you this method again over here on the second question about the y-axis. So again, I'm just going to emphasize my y-axis and x-axis. Sketch a complete graph. part of this complete graph is the original part of the graph. That's the original. Now my line of symmetry here is the y-axis. So let's do this again. Let's pick any point you want on this ray, such as this point right here. The point that is symmetric with respect to that. If I go till I hit the y-axis so it forms a perpendicular, I had to go 1, 2, 3, 4, 5 spaces. If I continue in that same direction, 1, 2, 3, 4, 5 spaces, notice it's perpendicular, put a point. That point has to be on my symmetric ray. If I pick another point, such as this right here, looks like I'm going, this is approximate, 1, 2, 3. So if I go 1, 2, 3, gives me a point. You only need 2 points to do this. But let's just do a third. This point here is on the line of symmetry, the y-axis, so it is right where it's supposed to be. So if I connect those points with the ray, I get the complete graph. Now if you can visualize taking this graph and folding it on the y-axis, the red and the green rays would be right on top of each other. C, which is Spanish for yes, symmetric with the line y equals x. Once again, let me first emphasize my axes. The y-axis, I've got the x-axis. It's a little better emphasis than before, it's a little thicker. Supposed to do a complete graph, so we have the original, which is here. Now the line y equals x is not shown currently, so we want to show it. So to show it, the line y equals x has a y-intercept of 0 and a slope of 1. So it looks something like this. When you draw your line of symmetry and it's not already on your graph, please do so that it's dashed. I'm just going to label it y equals x. Now, A and B were pretty simple. At least I hope that you felt that it was simple. C is not as simple. Let me pick points again that appear to be on this. I think we'll all agree that 0, 0 is on this graph. And we could debate about it, but it appears as though negative 5, 2 is on this graph, if my picture is drawn perfectly, and I'm sure that it's not. So, if I try to make a perpendicular, say I pick a point on this, such as this point right here, and I draw a segment that's going to hit this line of symmetry so that it appears to be a 90-degree angle. If I then take this distance, whatever it is, and I'm eyeballing it because I don't know what it is, and I extend it, it's going to end up being about like so. Notice, once again, this is not perfect, but this part is essentially equivalent to this part. I'm measuring there with this gray. That's about the same length as that. And then I could also say, let me draw that here. Then I could also say, well, this green part is basically equivalent to this green part. And it looks like it's pretty accurate. So I put a point there. I already have this other point, 0, 0, so I can connect those. So this ends up being in quadrant 4. Once again, it's not perfect, but if you drew this or thought it should be drawn in quadrant 3, it's definitely wrong. It's basically, if I were to measure this, if I were to annotate this picture so that it is quote-unquote perfect, the angle that's formed between this red ray and the x-axis would be the identical angle between the y-axis and this blue ray. Example D, the line y equals negative x. So again, let me emphasize my axes. That's a nice axis there. And that one there is quite lovely as well. Okay, I've got my original. Let's do a complete graph. So you have to have the original, and you have to also have the one that you're going to draw that goes with it. The line y equals negative x has a y-intercept of 0, a slope of negative 1. So it's going to look something like this. It's not perfect, but it's pretty accurate. So y equals negative x. What quadrant is this ray going to be in if it's reflected over the line y equals negative x? Is it quadrant 1, quadrant 2, quadrant 3, or quadrant 4? It's quadrant 2. Let me show you this. If I pick a point on this, once again, like this point here, and draw a perpendicular segment perpendicular to the line of symmetry, and then extend that same length in the same direction so that this is identical to this, puts my point approximately here. It's in quadrant 2. Once again, this point here is on the line of symmetry, y equals negative x. So if I connect those 2 points, I get a ray that looks something like this. Annotating this in a perfect world, we would be saying that the angle between the red ray and this line of symmetry is identical between the angle of this blue ray and this line of symmetry. I guess that's true in all these. Going back to C, instead of just saying the x-axis here and the y-axis, I guess just say the angle formed by the ray and the line of symmetry is identical to the angle of its symmetric counterpart. It's a good way to look at it. We got more symmetries here. There's a lot of words here, and it sounds confusing, but I assure you that you're going to be great at this, and you're not going to find it to be difficult, as long as you can memorize a few things. And I'm sure that you can if you choose to. First symmetry we have here is to the x-axis, which is what we just did, but it's giving you a rule to follow. xy is an element of S if and only if x negative y is an element of S. An example, if the ordered pair 3, 7 is on your graph, then the ordered pair 3, negative 7 has to be on your graph. Pick any point, the x values are identical, but the y value, if you change its sign from like a 7 to a negative 7, that point's also on the graph. Symmetric with respect to the y-axis, it's the opposite here. The y values stay the same, but the x value changes sign. So an example, let's say we have the ordered pair negative 8, negative 9, and that's on our graph. Here it says if you change the sign of x and make it positive, leave y the same, that point's also on your graph. If it's symmetric with respect to the line y equals x, this one here is so subtle it's scary. Notice it says y is equal to x. If you read it backwards, it says x is equal to y. So x becomes y because x is equal to y becomes x because y is equal to x. Example. Say we have the ordered pair 8, negative 7. If that's on your graph and it's symmetric with respect to the line y equals x, then you know for sure that negative 7, 8 is on your graph. X became y and y became x. This last one is a little bit more difficult. It's with respect to the line y equals negative x, if you read it how it says y is negative x. If you get x by itself, multiply both sides by negative 1, it would say negative y equals x. So we get two different things. One, you're saying y is negative x. Two, you're saying x is negative y. So that means if you have the point xy, such as, I don't know, 1, 7, it's saying then your x is going to become a negative y. So my x was 1, now it becomes a negative, what was y before? It was 7, it becomes a negative 7. My y becomes a negative x. My y was 7, but now it's going to be whatever x was, and you change the sign. It's a little confusing, but once you do this 3, 4, 500 times, it gets to be really, really easy. So example C. Seriously, you'll see this is pretty simple. I encourage you to spend some time reading the little notes on the right side here, especially this part right here. That's the meat that'll get you to promised land. It's the part that you need to memorize. So example C. Determine where the graph of each equation is symmetric with respect to the origin, x-axis, y-axis, the line y equals x, or the line y equals negative x. Circle all that apply. Let's check out the origin. For the origin to work, I'm going to write down a negative x, negative y. In other words, x becomes negative x, y becomes negative y. For the x-axis, I'm going to leave x the same. We're going to change y to a negative. For the y-axis, we're going to leave x the same. We're going to change the sign of x. We're going to leave y the same. For y equals x, we're going to make x y, and we're going to make y x. For y equals negative x, we're going to make x negative y and y negative x. So what does all this mean? Here's what you do. Take your equation, y equals negative 7x, and instead of using an x, change it to a negative x. Instead of using a y, make it a negative y. So it's supposed to be y equals. We're going to change the y to a negative y. Negative 7 times x. Instead of an x, we're going to use a negative x. Your challenge then, once you've substituted these in, can you manipulate this equation to make it look exactly like the original? If you can, then it's symmetric with respect to that thing. If you can't, then it's not. So simplifying this, notice this had y by itself. Let's get y by itself. Negative 7 times negative x is positive 7x. If I multiply both sides by negative y, by negative 1, I get y is negative 7x. Is that identical to the original problem? Certainly is. Therefore, this graph is symmetric with respect to the origin. Check out the x-axis. For the x-axis to work, I should leave x the same, but I should replace y with a negative y. If I can do that and get y by itself, and it's the same as the original equation, it's symmetric with respect to it. If it does not come out to be the same, then it's not. So y is supposed to be negative y. X is supposed to be x. Doesn't change. If I get y by itself, multiply both sides by negative 1. Negative 1 times negative 7 is positive. Is y equals 7x identical to the original? No. Therefore, it's not symmetric with respect to the x-axis. The y-axis. Replace x with a negative x, leave y the same. So y equals negative 7 times negative x. Negative 7 times negative x is positive 7x. Is that the same as the original equation? It is not. Therefore, it is not symmetric with the y-axis. The line y equals x. Remember, you read this from left to right and right to left. y equals x, x equals y. That's why I have a y here and an x here. So that means I take my equation, I replace y with x, I replace x with y. See, y is at the beginning, x is at the end. So y goes in for x goes in for y. This ends up being a negative, pardon me, I wrote this wrong. This should be a negative 7 times y. Please don't hate me in the comments because I made that mistake, because I will make lots of mistakes, ladies and gentlemen. To get y by itself, I would then divide both sides by negative 7, and I get x divided by negative 7 equals y. Is that identical to the original? It is not. So this graph is not symmetric with respect to the line y equals x. Y equals negative x, you read it left to right, you're saying negative x goes in for y. If you read it right to left, but first get x by itself, it would be saying x equals negative y. So in for x is negative y, in for y is negative x. So I substitute this in, negative x for y, negative y for x. Simplify it, negative 7 times negative y is 7y. Divide both sides by 7. This is not the same as the original. Therefore, it's not symmetric with the line y equals negative x. It could be that all these symmetries work. It could be that one or two work. It could be that none work. This particular problem is symmetric with respect to the origin only. Let me show you another example, because I know you are starving for it. We have 4x to the fourth minus 3x squared plus 8. So is it symmetric with respect to the origin? Well, to figure this out, we are going to take and put in a negative x in for x and a negative y in for y. We're going to simplify it and see if we get the same as the original. So we have a negative y equals 4 times a negative x to the fourth minus 3 times a negative x squared plus 8. Pause the video for a second, simplify this and see what you get. Here's what you should have got. This is a common mistake people make. They confuse order of operations. Some people look at this middle term and they say, I have a negative times a negative, so that's positive. That's incorrect. I mean, it is true that if you multiply two negatives, you get a positive, but order of operations, you do exponents before you do multiplication. So I got ahead of myself a little bit here. Here I have a negative x and it's to the fourth power. So that's a negative being multiplied by itself 4 times. If there's an even amount that you're multiplying, it's going to give you a positive answer. So this is 4x to the fourth. I'm going to bring this minus 3 down. A negative x squared is going to be a positive x squared. Positive x squared times a subtract 3 is a subtract 3x squared. This is the point where some people make mistakes. Exponents first makes this part here a positive times a negative is a negative. The original has y by itself, so let's get y by itself here. Let's multiply each term by negative 1, and then we're going to compare this to the original. Is this the same as the original? It's not. The signs are different. This graph is not symmetric with respect to the origin. X-axis. For the x-axis to work, x does not change, but y changes sign. So we substitute negative y in for y. Nothing changes with x. Get y by itself, multiply both sides by negative 1. It changes all the signs on the right side of the equation. Is that the same as the original? Most certainly is not. So it's not symmetric with respect to the x-axis. I am running out of space. Please forgive me for doing this, but I'm going to make this a bit smaller. I say forgive me because I know that you can't do the same thing on your paper. Don't hate me because you ain't me. That's the bottom line here. But you can be mad at me. I'll accept that. The y-axis here, replace x with negative x. Leave y the same. Remember, all these little q's are here. Now at first, you should be using those q's, but in a day, you shouldn't be. You have to commit this to memory. The symmetry things that we're doing here, we will literally use for the entire class. It's the foundation for what we're doing in this class, is these symmetries. So it's really important. Okay, so we are to leave y the same. We are to take x and change its sign. And I am once again running out of space. Let me pull this to the left a bit. Simplifying this. A negative x to the fourth is an even number of negatives. So each negative gets paired up. That makes it a bunch of positives. Negative x squared is positive x squared. Positive x squared times a subtract 3 is a subtract 3x squared. You'll notice this is the same as the original. It's identical. Therefore, this graph is symmetric with respect to the y-axis. The line y equals x. Reading this, just using logic, y equals x. Reading it right to left, x equals y. So y goes in for x, x goes in for y. When you substitute, use parentheses. Now the original has y by itself, so we have to somehow get y by itself here. Simplify this first. This parentheses have no value in this problem, but it is something I want you to do because sometimes the parentheses matter. This particular part doesn't. Now if you try to get y by itself here, you will notice your head exploding and possibly pus coming out of your ears. You ever notice how pus, it's just a disgusting word. I'm actually going to pause the video for a second so I can go wash my mouth out. Just from saying the word pus, it feels dirty. If you notice that you can't get y by itself, in this problem, I mean, I'm sure somebody can get y by itself. I don't have the skills to do it. To get y by itself here, I mean, really, I don't know how to do it. So we can see that this is not going to be the same as the original. I mean, in a perfect world, let's just say that this was y to the fourth and this part wasn't here. You're going to end up, you could solve that. You'd end up with y as the fourth root of something. There's no fourth roots in the original problem. So this is definitely not symmetric with respect to y equals x. Now don't cheat yourself. If you can get it by itself, you should. This one's not going to happen. This last one, y equals negative x. Y equals negative x. So make y negative x. Getting x by itself, x equals negative y. So replace x with negative y. So we substitute. Negative x, parentheses definitely matter for this problem. Once again, always do it. If you always do it, you will always do it correctly. If you sometimes do it, then you will sometimes do it correctly. I fudged up here, ladies and gentlemen. You're supposed to be y's, not x's. That's a funky looking y. It is funky. Negative x, negative y to the fourth is going to be positive y to the fourth. Negative y squared is going to be positive y squared. Multiplying that times this 3, which you're subtracting, is going to be subtract 3y squared and bring down the 8. And we could get x by itself here, but mean, what's the point? We can't get y by itself, which is how the original was, not symmetric. So this particular graph, y equals 4x to the fourth minus 3x squared plus 8 is symmetric with respect to the y-axis. Please pause the video and do problem number 3. Once you've unpaused it, then I would like you to check out my work. So the origin, we have negative x, negative y. The x-axis is x, negative y. The y-axis is negative x, y. Y equals x is yx. Y equals negative x is negative y, negative x. So the origin, I'm going to switch x, switch its sign. I'm going to switch the sign of y. Now notice this problem has x by itself, so I'm going to try to get x by itself. You could get y by itself here and then do the problem, but you don't need to. You'll get the same answer, but it's extra work that is unnecessary. A negative x is negative x. Negative y squared is positive. Getting x by itself, multiply each term by negative 1. We get this. Is that identical to the original? No. Therefore, it's not symmetric with respect to the origin. For the x-axis, leave x, change y. Negative y squared is a positive y squared. That is identical to the original. Therefore, it is symmetric with respect to the x-axis. I just noticed, this looks like a dude here. This right here is his eyeball. He's a little bit sad. He's got a little bit of a grimace here. And then you have his head. A little bit of hair up here on top. No? No one sees it? Alright, perhaps I need to get back to my psychiatrist if no one sees the little dude there. The y-axis, we are going to replace x with a negative x and leave y the same. Multiply both sides by negative 1 to get x by itself. I'm getting x by itself because the original has x by itself. Not the same as the original. Therefore, not symmetric with respect to the y-axis. Y equals x. We're going to put y in for x and x in for y. Now, you can probably look at this and say, if I get x by itself, it won't be the same as the original. That's great that you recognize it. Get x by itself, though. If you can do it, I'm telling you, you have to do it. Because if you don't do it, I will dock you many, many points. Many, more than you could possibly imagine. If I subtract 25 from both sides, I get y minus 25 is x squared. If I square root both sides, I get plus or minus the square root of y minus 25 is x. Not the same as the original. Last one. Switch your x's and your y's and their signs. So I have a negative y equals negative x squared plus 25. If I subtract 25 from both sides, I get negative y minus 25. If I square a negative x, I get positive x squared. If I square root both sides, I get plus or minus the square root of negative y minus 25 equals x. Obviously not the same as the original. So this graph is only symmetric with respect to the x-axis. Okay, we're almost finished. Let me give you a little tidbit here. There's a special name for a graph that is symmetric with respect to the y-axis. If a graph is symmetric with respect to the y-axis, then that graph is called an even graph. If the graph is symmetric with respect to the origin, then that graph is called odd. If a graph is symmetric with respect to the origin, it's odd. If it's symmetric with respect to the y-axis, it's called even. So why does that matter? Well, if you look on the next page, you get 3 more problems. But instead of saying, is it symmetric with all 3 of these, or all 5 of these things, like we did in example C, it's just, is it symmetric with respect to the y-axis, or is it symmetric with respect to the origin? Is it odd or is it even? Even, y-axis, odd, origin. So problem number 1, just to determine if it's even or odd. And you'll notice here this is y equals x to the 5th. That's what it's supposed to be. When I imported this, it got a little bit funky. Y equals x to the 5th minus 2x. So you're supposed to determine, is it even or is it odd? Or perhaps the third option is it neither. If it's even, it's symmetric with respect to the y-axis. If it's odd, it's symmetric with respect to the origin. For the y-axis, change x, you leave the y the same. For the origin, you change them both. Change both the signs of x and y. So is it even? If I change the x value to a negative, once again this exponent is a 5, it's not a 2. It's going to give me y equals a negative x to the 5th is going to give me a negative x to the 5th. Negative 2 times a negative x, or subtract 2 times a negative x, this is actually how it's written, is a plus 2x. Is that the same as the original? Certainly not. This graph is not even. If I check for oddicity, if that's even a word, if it isn't, it certainly should be. Someone please go to Wikipedia and type in oddicity and make a definition for it. Appreciate it. So origin here, we switch the y to a negative, we switch the x to a negative. Negative y is negative y. Negative x to the 5th is an x to the 5th negative. Subtracting 2 times a negative x is a positive 2x. If you get y by itself, you multiply each term by negative 1. And this gives you the same as the original. Therefore, this function is odd. Number 2, if you can't read it very well, I know I can't, this is supposed to be a 3, x to the 3rd. Is it even or is it odd? Even is the y-axis, which you switch x and leave y the same. Odd is the origin, x changes sign, y doesn't. So, is it even? I'm sorry, origin, x and y change sign. Is it even? We have y equals negative x cubed minus 7 times negative x plus 5. Negative x to the 3rd is an x to the 3rd negative. Negative x times a subtract 7 is a plus 7x. Not the same as the original, not even. Odd, change the signs of both. So I have a negative y equals negative x cubed minus 7 times negative x plus 5. So it's a negative y equals negative x quantity cubed is the same thing as x cubed negative. Subtracting 7 times a negative x is a positive 7x. Getting y by itself, I get y is positive x cubed, multiplying each term by negative 1, minus 7x minus 5. Not the same as the original. It's close, but this 5 here at the end is the wrong sign. So it's neither. This is his teeth. His teeth is neither. Happy. Last one. Even or odd? To be even, you change the x to a negative. Leave y the same. Negative x squared is a positive x squared. Same as the original. Therefore it's even. Is it odd? It's not. To be odd, you switch the y and the x signs. You switch the signs of x and y. And if it comes out to be the same as the original, then it's odd, but it's not. It's a booger on my finger. No, it's not. Thank you for your time.